been studying systems of differential equations of late. In particular, we've been focused on solving pairs of coupled differential equations that depend on constants a, b, c, and d, and whose solutions must capture a given initial condition. We can write problems like this in matrix vector form where A is a 2 by 2 matrix of constants. And we've already seen how to solve these problems when the matrix A has two distinct real eigenvalues. In this video, we tackled the two remaining cases. We'll consider how to solve the problem when the eigenvalues of A are complex, and we'll look at the case in which A has one repeated real eigenvalue. In other words, when the eigenvalues of A are real, but not distinct. Let's start with the case in which the eigenvalues of A are complex. Since we know they occur in conjugate pairs, we'll write these complex eigenvalues as A plus I times B and as A minus I times B. We know that we can also write an eigenvector corresponding to the first of our two eigenvalues as one vector of real numbers, say x, plus I times another vector of real numbers, say y. That said, an eigenvector associated with the other eigenvalue is x minus I times y. I'm going to the trouble of writing these eigenvalues and eigenvectors out like this because their pieces matter when it comes to stating a formula for the solution to our system of differential equations. Without further ado, that formula is this. Here, k1 and k2 are constants whose value is determined by a given initial condition. Let's now put this formula to work for us in an example. Consider the following initial value problem. It's not difficult to determine that the eigenvalues of the matrix featured in the given problem are -2 plus 3 times I and -2 minus 3 times I. With these eigenvalues in hand, we can use the approaches we've already studied to find the corresponding eigenvectors. For reference, here again is the formula we want to apply. To be clear, we'll take the various pieces for our formula from the first of our two eigenvalue-eigenvector pairs. Plugging these pieces into the formula, we obtain. Now it remains to find k1 and k2, and we do this using the initial condition provided. When t is equal to 0, the formula and the initial condition lead us ultimately to this system of 2 equations for k1 and k2. We solve equations 1 and 2 to find that k1 must be 1 and k2 must be -1. We then plug those back into the current version of our formula, and when we do, we obtain our final answer. This final answer can be rewritten as follows. If we plot u1 and u2 versus time, we see that their graphs oscillate. That is to say, they rise and fall. But ultimately, they tend to a limit of 0. We can also visualize these solutions in u1, u2 space. We know that the complex eigenvalues mean that the vector field connected to the matrix in our problem describes rotation of some sort. So, the path traced out by a particle placed on the spot described by the initial condition will be a spiral that passes through all 4 quadrants as it goes. What's perhaps not clear is whether that spiral will tend toward the origin or away, and whether or not it will be clockwise or anti-clockwise. We can see that because the real part of the eigenvalue we found is negative, the magnitude of the solution will tend to 0 as t grows. So, the spiral traced out by our particle will tend toward the origin. I suppose that's consistent with the picture we saw earlier where u1 and u2 both tended to 0 as t increased. To see whether we have a clockwise or anti-clockwise spiral, we can simply determine the initial instantaneous velocity of our particle by applying the matrix from our problem to the vector from the initial condition given. When we do this, the fact that the result is a vector of negative numbers tells us that the particle initially moves in a negative direction with respect to both axes. Ultimately then, our particle's path looks like this. We have a clockwise spiral toward the origin. Let's now move to the next case. Let's consider what happens when the matrix in our problem has a repeated real eigenvalue. Here's an example of the kind of matrix I'm talking about. It's a matrix for whom this equation has a double root. For the given matrix A, we can see this double root when we plug the matrix itself into the expression. We find that lambda is equal to 2 is a double root, or repeated real eigenvalue. But it's not just the repeated eigenvalue that frames this case. An equally important part of this case is that there's only one family of eigenvector associated with the repeated eigenvalue. Here, that family is represented by the vector v, which is 1, -1. So, although there are other cases in which eigenvalues repeat, they're not of interest to us here because the repeated eigenvalue in those cases is connected to more than one family of eigenvector. As an aside, I'll mention that cases of the kind we're ignoring can be solved by treating the differential equations in the given system individually, and we've already seen how to do that. In a manner of speaking, the problem that arises when a repeated eigenvalue is associated with only one family of eigenvector stems from the fact that there are not enough signposts to direct our solution. We can fix this problem and therefore come up with a solution by manufacturing another signpost. Let's call it W. The manufactured signpost cannot be an eigenvector of A, or else we end up right back where we started. To avoid this, then, we'll require that W satisfy this equation, an equation which no member of the family of eigenvectors of A could possibly satisfy. For the given matrix A, we find that this equation for W can be written out as follows. Just like with eigenvectors, we can exercise some choice when solving for the elements of the vector W. If we choose to set W1 equal to 1, for instance, then W2 must be equal to -2. So, we can use the vector W, which is 1, -2, as our second signpost. What we do now is use these two signposts to build a formula for the solution to a system of linear, homogeneous, differential equations that involve a matrix with a repeated real eigenvalue. The formula we build is this, where C1 and C2 are constants that depend on an initial condition. So, if we want to solve an initial value problem involving the matrix we just studied, something like this for instance, we can plug the different pieces we've uncovered into the formula to get this expression. Figuring out what C1 and C2 are exactly requires that we plug t is equal to 0 into what we have and set the result equal to the initial condition given. When we do this, we find that these constants satisfy 2 equations, which can be solved to give C1 is equal to 2 and C2 is equal to -1. Dumping these into our formula, we obtain the solution to the problem we started with. Incidentally, This can be simplified to give us the following concise form of the solution. We can visualize this solution in a couple of ways. We can plot u1 and u2 versus t like this. We can also plot the result in u1, u2 space, and to help us create such a plot, I'll lay down the family of eigenvectors. However, this family won't play an immediate role in our sketch. To construct our sketch, we'll place a particle on the point corresponding to the given initial condition. Then, we'll determine its instantaneous velocity by applying the matrix to the vector that describes its location, just as we'd done in a previous example. Carrying out the matrix vector multiplication shows us that our particle begins to move in this direction, parallel to the vector 1, 1. Next, we'll go to the other extreme. Rather than asking what our particle is doing initially, we'll ask what is it doing as t becomes large. As t becomes large, it's easy to see that this part of the solution begins to dominate. And so the vector u itself begins to look something like this. Roughly speaking, our solution is running parallel to the vector negative 1, 1. In other words, it's running parallel to the family of eigenvectors. Putting all this information together then, we get this picture of the path traced out by our particle. Let's now start to wrap things up with a recap. In this video, we encountered two formulas for solving linear homogeneous systems of differential equations. The first formula was built under the assumption that the matrix involved in the system of differential equations had a complex conjugate pair of eigenvalues. The second formula assumed that the matrix had a repeated real eigenvalue that was itself associated with one family of eigenvectors. The second formula relied on a second vector we called W. In both cases, we applied the formula we encountered to study an example, and we plotted the resulting solution. You'll know that you've come to terms with systems of two linear homogeneous differential equations when you're able to solve problems involving matrices with either complex eigenvalues or one repeated real eigenvalue. These cases are, of course, in addition to the case in which the matrix involved in the differential equation has two distinct real eigenvalues. We studied that case in an earlier video. Don't forget, you'll still be expected to use information like that expressed in an initial condition to solve initial value problems involving systems of differential equations. You'll also be expected to sketch out the solutions you come up with in u1, u2 space. It's not enough to just watch this video. Try some of the assigned problems to test your understanding. Read the course notes to better understand where the formulas we've encountered came from. Explain the origin of the formulas to a friend. Maybe devise a decision tree that would help you or a classmate figure out how to solve a given initial value problem you've not seen before. Basically, I'm saying don't be a passenger. Adopt an active role in your learning, and you'll master this stuff in no time.